Yeah, now this I have done on, I'm on cloud.
Okay, thank you so much. So hearty welcome to Dr. Atul Modi, and also we are very fortunate to have Dr. Elu Alia with us, who is the current president of Indian Association of Physics Teachers, and many other professors and teachers who are interested in Bloom's taxonomy. Bloom's taxonomy is what all of us are concerned with, but probably we do not understand it so very well. And then added to that is the another big word, constructivism. Everybody's talking about constructivism. Everybody's talking about Bloom's taxonomy. And teachers in school are expected to write their lesson plans, assessment, assignments, everything keeping in mind both the Bloom's taxonomy as well as activities taking care of constructivism, but nobody is sure what exactly is to be done in the classroom. So today we have Dr. Atul Modi with us. Professor Modi, I welcome you to this program because after a long wait of 3 years, I've been finally able to organize this program. So let me give a brief introduction of Dr. Modi. Dr. Modi is currently the lead instructor at Infinite Learning. Before retiring from VES College Thane as associate professor, he had studied MSc Physics in Indian Institute of Technology, Bombay. And then he did his Master of Science in Physics and Astronomy from Northwestern University, US. And he is someone who is deeply interested in physics education. And he has been working extensively on physics education for improving the quality of education. He has also trained many teachers. He is a subject matter expert at NCRT, and he's a serving member of NCRT committee for developing physics books and preparation for teachers training material. And he has been actively involved in talent nurture program in college and also in Indian Physics Olympiad training programs. He has developed many questions and experiments for preparation for Indian Physics Olympiad at Homi Bhabha Center for Science Education. And he's a very popular teacher who can make most difficult of concepts very easy to understand. So I welcome you, Dr. Modi, and I hand over to you.
Thank you, Pragya Madam. This is more than what I have sent you. And about popularity, I am not very sure, but I'll accept it. Okay, I'll just start sharing my PPT.
Yes.
Okay. Pragya Madam has already put title, which is slightly different, but this is my generic title. So it can fit into any brand name as you want. But basically what I have done is try to teach students physics by using problem as instruments of learning. Not a very easy way for students to learn, but it's a very effective way. And I have got fantastic results out of these methods. So what I'm going to do is I'll just go over through some philosophy as she has already announced, Bloom's taxonomy, constructivism, etc. Then I'll discuss about tools to achieve achieve it, and how to create these tools. Okay? I'll share some examples as time permits. So this is the plan. Okay. In education also we have 4 noble truths. One is there is a need for education. There is an objective for education. In fact, now there is a very important project which NCERT has taken up, which is called learning objective. So there is a need for education. There are means to achieve these objectives, and it is our job to provide these means. So this is the entire efforts in what we are going to talk about. Now, this most of the teachers must be familiar with about Maslow's hierarchy of need. Unfortunately, our education restricts to the lowest need, physiological. We just try to create education which is job oriented. Okay, the rest of the things are missing. And if Maslow was Indian, he would still have one more hierarchy at the top of the pyramid. And that's called self-realization. That only Indians can talk about. The Westerns did not know about self-realization. So there should have been one more hierarchy here. Now, these are objectives of education as per Bloom's taxonomy. I know many people would come up and say that, oh, look, the taxonomy has been revised. There are now new things and all. But I am an old man and I would stick to these old ones. That serves my purpose. Now, as Bloom's taxonomy says, this first is objective is knowledge. Now, here the knowledge is not in the sense we use as knowledge, as I understand, but knowledge is word knowledge is used as information. So most of our education restricts at the first objective only. Teachers provide this information in class. So something is there in textbook, we transfer it onto the blackboard, it goes into students' notebook, and finally into the answer paper sheets. That's the kind of examination we have most of the time. Now things are changing for good, so we are very optimistic. But that's where our education remains. Now, the remaining ones you can call as higher objectives. So that's a comprehension that is to understand the information and be able to use it, application. You analyze it, you synthesize it, and evaluation. And this evaluation should not be misunderstood as assessment. This is a self-evaluation. The learner evaluates what he or she has learned. So that's the perspective in which we should see. So what you call as higher order thinking skills actually are the 5. Number 2 to number 6 would go as higher order thinking skills. And unfortunately, that's not focus of our mainstream education. Now you have multiple intelligence as put by what the name. Anyway, so that's starts with linguistic, then logical, mathematical, spatio-visual. It should be spatial, not just spatial, spatio-visual, bodily, kinesthetic, musical, interpersonal, intrapersonal, naturalist, and the last one now which is added is spiritual. Okay. Now, as far as physics is concerned, we definitely need linguistic because the entire communication goes on linguistic basis. And I'm going to talk on problem-based learning. So even when a student reads problem and tries to understand, language has to come into picture. And of course, this theory of multiple intelligence says that all these more than one intelligence comes into play at a given time. Again, intelligence is a misunderstood word. It's more an intellectual ability rather than intelligence. But okay, we'll just stick to the traditional word use as intelligence. So when a student reads a problem, would analyze it by visualizing it, by logically interpreting it, then we'll try to put it in mathematical form and so on. So when actually we make a student do problem or solve problem,
I'm sure you've all been waiting on how to enter this level. And you can enter this level by running through
some
I
people are,
request all to kindly mute themselves.
yeah, some people are talking with their microphone on, so kindly mute that. When a student solves problem, has to use multiple intelligence at a given time, and would also actually enhance in the process the intelligence. There will be an enhancement of intelligence.
and be free from
Now here, what can a teacher do? So a teacher can create a more innovative and effective learning activities. So when I say problem, activities would also, a good activity would also qualify. Then a teacher. I'm really disturbed because
Chandni
people
ma'am,
continuously talking. Some people
it's
have their
Chandni
microphone on.
request Chandni Khanna ma'am to kindly take care of her microphone.
Okay. So teachers can contribute by improving and establishing better assessment methods. And some of these assessments may be carried out while students are in the process of learning or constructing their knowledge. What we actually broadly say as a formative assessment. But what is done in schools are not really this assessment, which the second point here on your screen. That's definitely not what we do, because we are all obsessed with numbers, and somehow students learning, we want to translate into some marks and some numbers, and that ends up not doing justice to them. Because what we are more bothered about is how would we admit students to the next level of education. And that's why marks comes into play. Otherwise, marks are something which is most unimportant in the process of learning, provided we have made sure that students learn by using new technology that most people would understand. When I say very sadly, I would say that up to class 12, we don't allow calculator for students. And it would really enhance students' capability to understand if they are allowed to use calculator. I mean, no political statements here, but laptops are being distributed, but nobody bothers that students who are doing physics should have a scientific calculator in their hand. By constructing, see, the teachers has to continuously learn and upgrade themselves. So by constructing his or own subject knowledge and teaching techniques that should percolate down, as in the first 4 points above. Okay, so most of the time, teachers progress stops once they become teacher, and thereby increasing his or effectiveness in one or more of the above mentioned ways, or any other way not mentioned. All right. So these are not definitely something which is written in a holy book. You can add to it. Now, normally when we talk about elementary education, our emphasis on students understanding and becoming aware of their environment and learn to observe things, or learn to classify things, learn to interrelate the relation between what they are observing in nature around themselves, and its importance to our life. If we go to secondary education, somehow, these things are not really emphasized anywhere. It just merely goes as some curriculum, some syllabus, and some topics. Then the importance of enculturation to the subject. Every subject has its own culture, its own way of thinking, its own way of analyzing things. For that matter, for example, if you see biology, I mean, I am very weak in understanding biology, but extensively depends on the collection of data and information. unlike physics, where with minimum data we construct the entire subject. So that's the enculturation to the subject. So you have terminology, you have diagrammatic representation, you have simple analysis. That's what we expect students at secondary level to learn. And higher secondary, of course, is a very different game. So when a student passes 10th and comes to 12th in NEP, of course, a lot of things are going to change. But then actually they learn to know more serious science in terms of physics, more serious physics, and how they start analyzing their observations. They learn higher order thinking skills and learn to apply to day-to-day life, to some other situations, etc. Now, actually, in literature, they talk about 3 ways of constructivist teaching learning methods. One is situated learning, cognitive apprentice, and problem-based learning. Now, if you know an uneducated vegetable vendor would also know how to do calculation because they have to deal with money. And they learn because they have to do their business. And it's not formally learned, but they learn. So it's a situated learning. They learn because they are in that situation. Then, of course, you work with somebody who is expert in the field, and you learn from by assisting them. And that's a cognitive apprentice. And what matters to us as teachers is problem-based learning, because we can create problems and situation where students would try to solve and learn the subject. Otherwise, if we say Newton's second law of motion, it remains just an information. So what I'm talking about in problem-based learning is switching, going from traditional method, which is teacher directed. So where teacher just comes to the class, teaches and delivers, students simply learn that content, and students are simply the recipient of knowledge. And then when you go into activity-based learning or problem-based learning, first is a problem motivated. Students are problem solvers, and teacher plays the role of coach. So coach is simply a mediator, just creates an environment in which students actually construct their knowledge, their understanding. So the focus is on students, what people call as a learner centric. But it's not possible without a teacher to create that environment. So it's not to take away importance of a teacher. It's actually giving more importance to teacher's role. But the learning process is a learner and not teacher centric. So it's not as a teacher we solve a problem on the board and students learn, but it is we give them an environment and facilitate their learning by making them solve the problem. Sorry, my animations are not working well, so sometimes it will just flash all the points simultaneously. So first is what do we achieve when we actually make students do problems? So first is that we can make them appreciate the theory they are learning. Uh, we also teach them to look at the symmetries in nature, be it physical, be it geometrical, or even abstract mathematical symmetries. Then there are, of course, interdisciplinary type of problems where you learn to apply to other disciplines, the techniques and the knowledge you learn in your own subject. Or we also introduce higher level facts through problem using lower level physics. So simple facts which teach them the basic physics, but we can still make them construct. In fact, I must point this out. If you see most of the scientists, the way they think about it, they always think about in terms of basic physics. Okay, the nobody actually starts writing equations. People start thinking about what happens at the most simplistic level in basic physics. So even the higher level problems actually are approached starting with the basic physics, learning, understanding from the first principle. So we can, since we are teaching first principle, we can always expose them to higher level through problems. We can make them do order of magnitude calculation. because many times students don't have an idea or an estimate of what these magnitudes are. For example, we talk about high energy physics, and we talk about energies of particles in terms of GeV and TeV and so on. But if you realize that a cricket ball, which is bowled by even a medium fast bowler, would carry much more energy than those energy. So although we call it as a high energy particles, okay, those energies are much smaller. I mean, so that order of magnitude and the understanding should come. I mean, this is the most elementary example which I'm talking about. Then, of course, we can give them an open-ended problem so they can think about it. Nobody expects anybody to solve open-ended problem, but at least it initiates the process of thinking in them. There are always problems which are unsolved, which even the scientists are working, but can be introduced to students at a very introductory physics level. So that process of thinking about that problem gets initiated at a very early stage. So at every stage they are learning, they will try to correlate and try to see how they can understand what is happening at the forefront levels. Okay, and of course the applications are always at the heart of learning any subject. If we cannot make use of what we learn for good, then it's of no use to learn. Okay, so problems actually strengthen mental abilities. Uh, uh, and once students can correlate this principle, observation, even the experiments, they can understand better. Their understanding of the experimental techniques, uh, even they can design an experiment if they understand principles and observations better. All right. So basically, as somebody has noted, Brownstein, the learner should constantly be challenged with tasks that refers to skills and knowledge just beyond their current level of mastery. This will capture their motivation and build on previous success in order to enhance confidence. Now I'm saying so many things, and I'll point out something more interesting after we read what Richard Feynman says. So if you look at the preface of Feynman lecture series, he says, I think one way we could help students more is by putting more hard work into developing a set of problems which would elucidate some of the ideas in the lectures. Problems give a good opportunity to fill out the material of the lectures and make more realistic, more complete, and more settled in the mind the ideas that have been exposed. Now, at this point, I would like to actually point out the reason I am doing this is that one of my daughter was doing applied art, and what they have to do is when they go to the classroom, a teacher just puts that today's their activity is this. So either they are doing sketching or some drawing or painting or whatever they are doing, whatever they have to create. Almost entire day they're just busy doing that work, and teacher just takes the round, intervenes, discusses with students their ideas, and probably guides them for doing things better in their own way. But basically the whole focus is on students doing something and learning, and not teacher. I mean, imagine a drawing teacher would just go to the classroom, draw something or paint something in front of students, and then said, okay, now you know how to do this. So in exams, you come and do this. But in physics, that's what we do actually. As a teacher, we go to the classroom, we talk a few things, we dictate few things, we do problems on board, and then students just have to prepare for exam and go and give the exam. So actually, in real sense, that learning never takes place in a traditional methods. What we are employing, what I'm talking about, is from physics perspective. Now, she has also talked about Bloom's taxonomy and constructivist. So I had to actually bring in these slides. There are 6 principles we are talking about in this. One is the first is the constructivist principle, which says students construct their ideas and observation, pulling together what they see and hear into a mental model. So when we put things in front of students, students have their way of visualizing, imagining, and you will find many of the times they have taken it not in the right spirit. And then we do not have a way of correcting that. Okay. The best thing they do is just memorize those sentences and rewrite in the exam. So unless you challenge them or you make them speak or apply it somewhere, you do not know where they are going wrong in their ideas, in their mental model. Okay. So this is Piaget's individual constructivism principle. The next is context principle. Says it's reasonably easy to learn something that matches or extends an existing mental model. So something which matches with my experience is very easy to understand. But if it doesn't match with my experience, then I have a lot of difficulty. The simplest example, which most of you are physics teachers, so I understand that you are all at least post-graduation, have a post-graduation in physics. So you know that quantum mechanics turns out to be the most difficult to comprehend because it's not what we have ever experienced. The next is change principle. It is very difficult to change an established mental model substantially. And this also you can understand. People found it very difficult to switch from classical to quantum ideas. Even now, as a student, we all find it very difficult to adopt to quantum physics. So the principle 3 is very easy to understand, but you can think of this in terms of basic physics, that if a student has not experienced something in their real life, they would find it very difficult. I mean, everyone understands in terms of Newton's first law of motion. All right. All the motions we see in our real life stops if they are left on their own. Whereas Newton's first law says it would continue to remain in state of rest or uniform motion. So that's the first thing where your observation, your experience, and your mental model does not match, right? So it's difficult for students to comprehend that. The next one is the distribution function principle or individuality principle. So construction of knowledge is always individual. Teachers only facilitates. Okay, it is students who construct based on what we present to them as a teacher. They construct their own mental states based on their own experience, their personal thinking. And the different students have different way of learning and visualizing. In fact, if you look at the mathematical tables, even 1 to 100, people have different way of visualizing those numbers, or when they carry out their process of addition. In fact, if you discuss with your students or colleagues how they actually carry out addition and they think about it, or they visualize it, that's what makes some students better with mathematical operations than the other students. So that's a very simple example, that people have a different way of visualizing. Although we are teaching same mathematics to everybody. We teach them 2 plus 3 equal to 5, 15 plus 9 is 24. But students have a different way of going from 15 to 24. So that is very interesting. I welcome all the people to find it in their own way out, how different people think. So to this principle, these 4 were Piagetian principles. To this, we have added 2 more principles. One is communication principle. So when we learn, we should be able to communicate to people. Otherwise, people would not know what we have learned. So similarly, here, I mean, what we expect is when student learns, they should be able to communicate to us what they've learned. Otherwise, we would never know. And unfortunately, the standard examination do not actually test what their communication. It just takes test how much they have memorized and then reproduced in the examination. So that's where this doesn't come into picture. Then principle of scaffolding and enculturation. So as I said earlier, that every subject has its own culture, its own way of thinking, visualizing, its own jargons, formalism. So while students are trying to develop this new knowledge, they construct this new knowledge, they need scaffolding and enculturation. We'll come to scaffolding part. The problem that we give them is sort of an enculturation, but what we provide as a support when they are trying to solve problem is the scaffolding. So we need to provide them enculturation and scaffolding. That is the role of a teacher. So constructivism, if you take out of the education, there is no role teacher has to play. In that case, you can put all your lectures and study materials on internet and expect students to learn themselves. We all know what is happening because of the online education. So that was a learning experience for all of us, whether we agreed with or not. And so we can improvise upon it, or we can understand the limitations of what internet provides. Now, the social constructivism, the last two principles we talked about, actually has come from Vygotsky's social constructivism. And in Vygotsky's social constructivism, he has this concept of zone of proximal development, which is the distance between actual developmental level as determined by individual problem solving and the level of potential development as determined to problem solving under adult guidance or in more capable peers, which is termed as scaffolding. So if a student is left on their own, they may be able to solve problems, they may not be able to solve problems. Sometimes even if they solve problems, some of the finer details they may miss, unless there is a teacher who is there to actually question them and bring them onto realizing some of the finer intricacies. Or sometimes students learn when they are working with more capable students, their own classmates. And that actually is a more important learning experience than what happens between teacher and student. So this zone of professional development is the advancement of student, which would not take place unless you expose them to this scaffolding. It means expose them to this problem solving with the guidance of a teacher or collaboration of capable peers. When I say collaboration, people misunderstand. If it's a big project, people collaborate. But if it's a small problem solving related to what we are teaching, then the collaboration should be minimized, because otherwise ends up some big students copying from brighter students. But if they are made to do individually, but allowed to discuss with each other, then they would learn much more. So all this scaffolding for helping students to advance in their zone of proximal development is guiding students to create appropriate visualization or mental picture, or pointing them to precise auxiliary problems. Sometimes students don't understand the problem. They fail to see the problem in totality. Then we have to give them a smaller problem. We have to help them break this problem into smaller pieces, try those smaller puzzles to solve. And once they can comprehend those smaller ones, then they should be brought into a larger issue, which they would be able to do better after they've been exposed to these auxiliary problems or auxiliary activities. I mean, for example, some problems actually we ask students to go and do something, sort of an experiment to actually visualize what is actually happening. They may do it, or they can mentally also do same activity, and they would many times, most of the time, come out with the right answer because they derive from their real life experience. Sometimes you have to create cognitive conflict in their misconceptions. So if they have a wrong conception, instead of feeding them the right concept, we create situations where their concepts fail. So that creates a conflict in their process of thinking. So we can feed them the processes through which they understand where is the policy in their own understanding. And then we can give them situations by which they can actually understand the concept in the right way, instead of telling them what is the right thing. That is the way we try to construct. Also involve them in a reflective metacognitive discussion so as to arrive at strategy to solve problem. Okay, so this is all a part of the same process. So one or more of these would be used at the same time when a teacher actually makes students do problem. So when we say problems, typically if we see, many of the times problems means in physics, people misunderstand problems as just take some numbers and plug in a formula and find something. So that's not really called problem. They are just plug-in problems. Okay, just estimating something numerically. Problem actually means that something that involves basic principles, which is attractive enough. In the sense, when I say attractive enough, means one should really feel interested in solving such a problem, because if somebody is genuinely interested in learning, should be definitely attracted into looking into the problem, because that enhances the learning. Problem should also be rich in context, should be sufficiently difficult. Otherwise, it's not problem. But it should not be difficult that students can't solve it. Then there is no point in doing it. So one of the idea which I just expressed in the earlier slide was, student find it difficult, then we actually problems, the smaller ones, the easier ones, through which they can start building upon their understanding to approach the more difficult ones. It should require steps that are not repetitive patterns, and at the same time should involve some decision making. They should be able to make decision whether I want to do this, I want to do that, or I want to use this idea or that idea. Sometimes students use wrong formula to do a problem because they misunderstand. I have seen students making blunders between AC circuit. Okay, so that is a simplest example of decision making that one should understand. A problem should have a reasonable goal, and at the end, problem should guide students to comprehend what you are trying to make them learn or its application. Then how to create this kind of challenges or problems, and how to know whether they would achieve our objectives. So these are some of the criteria. Of course, intuitively, most of the teachers definitely know what actually we mean by problems. Most of the practicing teachers definitely understand. So this is just the educational process of communicating in words. So sometimes a problem should cultivate real world challenge. It should cultivate higher order thinking skills, problem solving skills, interdisciplinary learning, independent learning, information mining. I mean, the latest word today people use is data mining. In this case, we are saying information mining. So internet has exposed students to vast amount of literature and information. But if they do not have that capability to read and understand, it is not of any use. So when we actually uh, uh, teach them these problems and they learn how to solve these problems, eventually they should be able to understand the information which they are being provided from various sources. That could become source of their learning, because for a teacher it is always a challenge. We can't bring everything under the sky into the classroom. There are all sorts of restrictions and limitations we have, but we can prepare students, right? As they say, you don't give them a fish, you teach them how to fish. So if you have made them capable enough to be able to solve problem and understand, you have encultured them enough to understand the language and the process of thinking, then the information they would get, they will be able to understand and make sense out of it, or make use of that information. Of course, teamwork is and the communications. So unless a student actually can solve problems, they would not be able to communicate. I found this. Most of the students find it very difficult to write even 2 or 3 sentences on their own, because all the time they've been just reproducing what is in the textbook. But when they start solving problems, then they have their process of thinking and they will start communicating. So that becomes a very important process. Now, how do we design a problem? As I said, most of the time for teachers, intuitively it is understood, but this is just an academic exercise. So first is you identify the area of the subject, sub area, underlying concept, what we would like to highlight, okay, what we would like to students to understand in terms of application or its usefulness in learning that process. So once this is done, then of course the goal of, yes, hello, somebody said
Sir,
something.
yes, sir. Aradhana, this side. Sir, can you go back to the previous slide? I need to take the screenshot.
Okay. Yeah, let me know when you're done. In fact, I forgot to say, somehow online, I'm very reluctant, but the time has taught us that we should be getting
Yes.
into the online part. But if it's an interactive session, it's more effective. So although ideally in an online mode, interruptions are not very comfortable, but if somebody has a question to ask, kindly point it out. Otherwise, at the end, we can definitely address whatever people want.
Actually, this online mode is teaching us to understand the student's perspective also, that how effective the learning goes. So here, when we are sitting in the mode of a student, it is giving us a reflection that when the content delivery is going, how much remain in the head. So it will be great for us to introspect.
Great. All right. So once this is done, identify the goal of the problem in accordance with why a particular problem was set up, and interrelation with the equation, the application. Problems may involve some goals, may involve concepts of a different area. You know, within physics itself, if we have an object moving in electromagnetic, we use mechanics also, we use electrodynamics also. So the interconnection between different areas and sub areas of the subject. Care also needs to be taken that the goal in the problem should not be too obvious. Otherwise, it's not a problem.
There is one comment in the chat. Can we get some inputs on how some exemplars with actual content to be used and transact the same in the classroom?
Yeah, as I said, after I finish this, we will come to some examples.
Yes. Okay.
So this is a mechanism of problem solving. So when I said provide scaffolding, we give them problems, etc., etc. Then this problem, if problem is difficult, then it can be broken into parts, as I've already mentioned. Then we develop auxiliary problems, and students should be guided to solve these auxiliary problems, and then made to come back to the original problem, and then use their understanding of solving the smaller problems into solving a more difficult one, which they found it difficult. Okay, so it involves guiding students to create appropriate visualization or mental picture, pointing them to precise auxiliary problems, sometimes creating on-the-spot examples, questions, challenges, or conflicting ideas for them to really do some thinking about their own way of processing information. So involving them in reflective metacognitive discussion so as to arrive at a strategy to solve the problem. So this is about the mechanism of solving problem. Now, this is an example. So as somebody has pointed out, I'll tell you, this is a problem from book of Herodotus. And let me tell you, when I conducted a problem-based learning workshop for undergraduate students, those students who came very willingly to attend the program, we went on for almost a month with the problem solving. Many of them took one day to solve this problem. And I'm not going to discuss the solution of the problem. So you forgive me for that part, because the purpose of this lecture is completely different. But you would understand that although those students have passed 12th standard exam and they've come to do undergraduation in physics, they really have a difficulty, because this kind of process they are not exposed to, they are not used to thinking, they have not been trained. That mental ability has not been strengthened to deal with this kind of. So the way we built our physics by exercising, this problem actually helps students develop their mental faculty, enhances their mental faculty, their abilities. So when they found this problem difficult, we gave them two auxiliary problems. The first one, of course, was a problem in Halliday Resnick's book. It's a very simple problem, actually. Mostly, these are the kind of problems which are typically used in textbooks and examinations. Okay, so but these become the auxiliary problems, and once they understood some of the crucial concepts, we could communicate to them when they solve these easier ones to go to the higher problem. So teacher's role here is to engineer process of learning. Okay, many of us teachers, especially those who have done science, sometimes feel that they should know engineering. So we are engineers actually for students' learning process. So we design the experiment, we design our teaching, and we design their thinking process, students' thinking process.
So here the raising the question which make the child to think and reflect what the outcome is planned to come may initiate the process of learning.
We initiate the process of learning. That's correct.
So that the way we can think that we are engineering. That's
Yes.
why the education should be one-to-one interaction, not a mass or crowd learning. Because when you are doing in a mass, you are not handling individual, maybe at different pace.
That's correct. Okay.
Sir,
Yes.
sir, so by PBL, problem-based learning in physics, do you mean that more of the numericals that are given in the books, in Erodo and other books, they should be taken up to teach the concepts
No,
rather
we are not
than
talking
the
about quantity. We are not
derivations?
talking about quantity.
So what? Okay.
So when we say we should make students do, right?
Yeah.
You see, time is an issue here. See, as a teacher, suppose if I am teaching, I would be teaching 1 or 2 subjects at a time. Students have to learn 6 subjects at a time. And sometimes we fail to understand that aspect. So when people say, you use this book, you try all the problem at the end of the chapter, we are being very cruel. Eventually, students will not do anything because they will start lagging behind in learning next chapter or other subjects because they have been dumped with so much of work at the same time. That's not what we are talking about. We are talking about quality of learning. So, in Hindi, there is a saying, ek ke sade sab sabta hai. So, if they learn one problem in its totality, they would have understood everything. So, later on, anything else you give, they would be able to manage. Yes, definitely, they should do some practice. So, teacher have to really use their discretion and give students the amount of activities, exercise, or homework which they can manage on their own. Otherwise, this is a classroom activity. This is an interactive. When I say problem-based learning, it's very much an interactive activity. It is not a homework activity. I can't tell students, you do this problem, and if you have difficulty, then do these 2 auxiliary problems and then come and do it. No, I mean, it's an interaction between a teacher and student or amongst the students. In fact, that problem-based learning classroom is not a quiet classroom. We have a concept of classroom with a pin drop silence. No, it doesn't. Learning doesn't take place if there's a pin drop silence. Learning takes place when students are very active mentally. So we are not talking about giving them entire Erodo book or this book or that. No, no. Very precise activities.
So, sir, is our task as teacher is to find problems which involve lot many concepts together, and student has to search for the
Not
data.
necessary lot many concepts together, but they should understand the concept in its in a broad aspect, not just in terms of words or a very narrow example which we give. They should be able to understand that how this concept works in different situations. Our aim is that, okay, it's not that in this world you can create 100 different situations where Newton's second law applies. You can't make student do 100 problems, but you can make them do just one or two such problems so that they would understand that how it works, and then any new situation arises, they would be able to analyze in the perspective of what they have learned.
Okay, sir.
Right? So what is the benchmark for effective learning? I'm leaving this. I'm not answering every question. Okay. We also want to keep pace with development of science and technology. So many things have to be revised. Many things have to be kept as it is, because things are always evolving. So, for example, when I was doing my undergraduation, we were still being taught vacuum tube technology when it was out of date. There were already semiconductor technology, which was everywhere used. So we have to keep in pace with development. But unfortunately, most of the board of studies or syllabus framing bodies would meet once in 5 years. And today we know that in electronic industry, things change very rapidly. Okay, so even though now it's a very high time students should be made to use calculators, we still actually expect them to do calculations without using calculator. Okay, and computer, of course. And today, actually, most of the students have access to calculator and computer. Everybody carries a mobile telephone. Okay, so mobile has a tremendous computing power. 20 years back, when I bought my first computer, is much weaker than what my
तू कहाँ रहेगा तुमको छोड़ने वाला कहाँ हूँ मैं
all right. We can also actually touch upon, I mean, this, nobody has to tell a teacher that you have to go and teach this new development. Okay, those developments are not touched upon in this syllabus or curriculum. Teacher can always use and expose students to those ideas, and see the excitement and the direction you give them for their own career growth.
कुछ ठीक चल रहा है सर
Somebody is talking, kindly keep your microphone off. So personally, we have to keep in pace with development of knowledge and motivate students to keep development. And many times we find it doesn't happen with all the students, but we always find students who are so much hungry for knowledge and learning that they keep track of things, and they come to the class or individually they approach teacher and say, look, this is what is happening, this is, so we learn from them, because we also have limitations. So there are things which are happening in the world, new technologies are being developed, new science have been discovered. So sometimes students come and share their what they have learned about it. So, but that for that we have to create that kind of motivation. So if they have a confidence that they understand what they are doing, then they will be able to go in that direction. Every stage, the knowledge has to have some practical applicability. So when we teach about electricity, unfortunately, we say that we are science students. I must say this. When I was a student myself, and I told somebody that I am going to do physics, then he said he was very highly placed in some company, a very big company. And he said physics वाले students को कुछ नहीं आता. He said when I interview वो तो एक fuse भी replace नहीं कर सकते हैं. So we teach them all the concepts of electricity, but when it comes to household electrical issues, we have to still call a local electrician who may not even have completed his schooling. So the practical aspect is always kept aside. And then, of course, we have some new name for it. We call it as a technical education or these and that, and it's not part of our science curriculum. I mean, who says that whatever is the application of science should not be there as a part of science curriculum? So household electricity is never covered as part of our syllabus anywhere till they graduate. I mean, I had a classmate, so not a classmate actually, he was my friend. I met in USA, and he said when he joined his first year of engineering, and his father's scooter would not start. Then he took his permission from his father, and he said, "Daddy, can I try to fix this up?" And he started thinking, using his thermodynamics knowledge as to how would a scooter run. And then he said, from the first principle, I started checking different part of the engine and the mechanism of starting and igniting fuel. And then he could actually fix the problem. Of course, the greatest joy was gone, and his father was extremely pleased with his son's ability, which he had achieved. I mean, not that he was taught even in engineering college how to repair a scooter, but he used his basic understanding. Now, that kind of understanding we are not able to impart to our students. Okay, when I say street smart, that is the kind of example. I mean, you see, Americans had this satellite technology, and we could still block their viewing when we prepared for Pokhran explosion. So that is a street smartness. So even in absence of technology, people should be able to achieve their goals. All right. Teachers need to keep thinking, learning, grow in intelligence. This is for teachers, definitely for teachers only. This may percolate down to students. So basically, we have to discover joy of learning. If I don't enjoy physics myself, my students would never enjoy. They would not be able to sense that there is a joy in doing physics. Now, this I have already mentioned that many times I say that I have 20 years of experience. But is it 20 years of rich experience or 1 year of repeated 19 times? That's a statement. So we have to keep growing year-wise. Every time I should be learning new things. I should be improvising. I'm not just doing same thing year after year. Doesn't matter, the textbooks may be the same old textbook, but I should be growing in my knowledge, and I should be able to bring that down to students. Yes, now how to create this? The simplest way is, you look at some of the competitive exams. Sometimes they're very interesting and very nice problems. I'll show you one example, but there are very, very interesting problems. Even in CBSE exams, sometimes they ask very interesting problem, which actually test students' understanding of so many things simultaneously. I mean, sometimes they simply give a graph and say, okay, now you tell me what will be this, what will be this. And so they have to actually interpret, and they have to analyze the equation mentally to understand what this graph is reflecting. Okay, I found one such problem. I have not included here as an example. So, junior science Olympiads, physics Olympiads, sometimes state level entrance exams, national level exams like JEE, NEET, etc. Sometimes they have a very interesting problem. I am not saying every difficult problem becomes a good problem for learning experience. No. Okay. Maybe putting little efforts, you will tend to realize what actually gives them a lot of learning, and what is just a sort of a difficult exercise to go through. So we are not going to say that by putting them to do a problem, we are actually making them to solve difficult problems. The idea is not to expose them to difficulty. Idea is to make them understand physics in the right perspective by experiencing this challenge. So artificially made complicated problem may be a good problem for an entrance exam, but that's not a good problem for learning or testing students' knowledge.
Actually, in entrance, the major objective is discriminating because you have a huge lot. Out of that, you have a limited number to be screened. So their objective is not testing learning level, but discriminating based on the learning achievement or problem solving skill. So the
Yes,
two objective is quite different.
I agree. That is why I said that this competitive exam sometimes may give you a very interesting problem, which you can actually adopt. This is the last point. It says sometimes we can slightly modify to suit our requirement. Okay, I'm not saying that competitive exam problems are good instruments for making students learn the subject. No. Okay, as you said, they have a different purpose. We have a different purpose. Okay, so when we say problem-based learning, we are not there to actually judge at the end of the year who is more intelligent, who is less intelligent. When we are using these problems, we are actually helping students to enhance their intelligence, learn the subject in the right perspective. Okay, our purpose is different, but these are good candidates. Some of these problems.
Our purpose is diagnostic, so that we can know where the child is lagging.
No, our purpose is not diagnostic. Diagnostic is a necessary evil in the education system. Our purpose is to help students learn. Simple.
Yeah, but when we are solving model problems, so there is a two objective. One, making the child and judging the child is a learning competency. At the same time, some lack of competency may give teacher to understand that this is the area where I have to invest a little more. So that the sense I'm saying little diagnostic.
See, when I'm talking about problem-based learning, I'm not talking about education in totality. I'm just talking about one particular aspects of learning.
Okay, sir.
Okay, so as I said, the assessment is a necessary evil. I'm not addressing the question of how do we assess, the philosophy of assessment, and what should we do. Okay, in fact, if you remember, I said that this assessment has created these numbers, and then we get too biased with those numbers, and we don't look at. And sometimes you will find that students who have not been doing very well in their school and college have actually exemplarily done well in their career as an engineer or as a scientist. So our numbers are not necessarily proving right. But that's okay. We are not challenging, debating anything. We are just talking as a teacher, what can we do to help students to understand the subject? Okay. Especially the subject like physics, which everybody finds it very difficult. And if I am saying that I'm talking about problem-based learning, I have never said anywhere I'm making subject easy. In fact, it is still challenging, but I'm only supporting students learning and supporting them to accept this challenge. Okay, so I'm actually helping students to reach a stage where, I will give you an example. I met one of the leading university engineer, graduated with 75%. And he was working with a very meager salary in some local industry. And I said, if you just write GATE exam and go and do your MTech or PhD, you would get much more as a stipend. Then he said, I am not confident about writing GATE exam. Now, this is what I'm talking about. He's not even thinking of accepting as a challenge. See, appearing GATE exam and failing is a secondary matter. He's not ready to even try that because he doesn't have that confidence. We have never exposed them to face that kind of challenge. So when we say problem-based learning, actually, one of the cognitive aspects is belief system. The students don't believe that they can do it. Our students, normally, they can only reproduce. Okay, when you say that I am a teacher and I'm going to teach, they expect you will go and deliver. You will perform on the platform. Okay, nobody thinks that teacher has to do much more work if they want students to perform. And what we have to do is to make students perform. I don't have to perform. And when students perform is my performance. So the purpose is completely different. So I'm not talking about competitive exam or assessment part. I'm saying sometimes they have problems which can become good candidate for using for students problem-based learning.
Sir, can we just simplify the things? And is it right to say that we are focusing on making student competent in every aspect of life? Like a person who is a physicist or a student of physics, like at this age, I am also still a student of physics, and throughout the life, I will be definitely. As we keep on learning many new things with these childrens, they are much brighter with the mind as they are coming up. So what I feel is just to make a student competent, that he is able to describe what he feels about that problem, or he is able to evaluate or discuss what question has been asked to him. So then what happens, many times it's not just about scoring marks. Actually, he has understood the problem. Maybe numerically he is unable to academically score the marks, but theoretically, or when applying that knowledge while sitting in a cabin or on the field, he is more efficient than a person who has just been an academic scorer, because he was someone who had just understood and has written the theory part. But the other person who is more competent, as well as he is having good concept, was unable to write the answer probably, but is having good concepts. So is it that we are focusing on, that building more conceptual knowledge for them, that they have confidence to apply in real life, not rather or merely bounding themselves within a classroom with a piece of paper as a certificate of their knowledge?
Yeah, okay. With a very simple statement, I will try to clarify it. The reason Sachin Tendulkar was so successful because he enjoyed hitting the ball out of the ground.
Right.
Simple. So if a student enjoys doing what he is doing, then that will lead him to all kinds of success. As a teacher, my goal is not to see that he succeeds. My goal is just to expose him to that joy of doing physics. Just kindly excuse me for just. Yeah. So, and then the second part, see, it gets addressed into the slide which is there in front of you. Unfortunately, that is not what is our aim of assessment. It's not just the competitive exam, but our school college exam also doesn't address that. So when I say that the goal of problem solving instruction is to improve cognitive process of student when they are confronted with a novel problem, then the goal of assessment is to describe cognitive process which are used in problem solving. But that's not what we do. So that's why I'm saying that the practical aspect, I'm not going to make much comment, because that's beyond what I can do to the system. But what I can suggest to a teacher is that even one problem per chapter, if you can make students do in this particular manner, in that spirit, and they learn to enjoy, at the end of the year, if you have taught them some 15 chapters, they would have learned to do 15-20 problems in that spirit. And then they would have definitely developed their intelligence, thought process. It would slowly build up. Okay, so it depends on the limitations. People will have all sorts of excuses, reasons, rules, regulations. I'm not going to challenge those parts. I'm done with those
So may I say
challenges.
something? So like just now we had 2 points, Sachin Tendulkar and system. Now Sachin Tendulkar, you just said if the child has this, he has interest in that, he can do whatever he wants to do. But now if you talk about system now, I'm just talking about from class system. System has made the science or the physics or the chemistry or bio to, degraded the science in such a way that they said, okay, what they say, if child has to study science or he has got when he can do it on his own when he come to class 11. Until class 10, they have decreased the science, the standard of the science to such an extent that when they come to the class 11, they are not able to do as good as they used to do when the syllabus was quite sufficient, quite good. If you talk about, say, about 10 to 12 years back, the sufficient syllabus of class 9 and 10 physics syllabus on the science was quite good. Then they were able to do good well. But now it has been decreased to such an extent by the system. So how will you say, how can we say the physics Physics needs understanding. If they do not understand the concepts in class 9 and 10, how will they apply? Please.
Yeah.
Sorry, thank you.
No, that's fine. I understand. So when I said I am done with the system, that when I am saying that, I really don't have to report to anybody to do anything. All right, but most people have their jobs, and your jobs, whoever has created that job for you has some purpose. And so no matter how, as a teacher, what you perceive it, you will have to satisfy those requirements to earn your living. All right. So you have to strike a balance. And that is an individual issue. I won't be able to address it here, but I will definitely give you an example here in these coming slides where it would be partly addressed to what you said, that the syllabus is reduced and students are not prepared when they come to 11, 12. But if you have tried this problem-based learning kind of process, constructivist process, students will definitely be able to meet the challenge. Somebody already pointed out that those students who don't do well in your mainstream eventually end up doing extremely well. That's because their learning was not broad-based, or they didn't try to accumulate too much of knowledge, but they probably focused on that whole process of thinking and being able to apply it somewhere. So if that is our aim, then students will adopt to any situation later on when they encounter. So just wait a couple of slides down, we will be able to see. So we can supplement regular curriculum with day-to-day applications. Our movies, Hindi or Hollywood movies, they have a lot of action sequences which involves physics. Whether it is violating physics or whether it is possible can also become a very good analysis for students. You just show a clip and tell students that tell me whether this is possible or not, and under what circumstances this can happen, what kind of things required, what kind of strength, whether it is possible for a human being to achieve it. Equivalently in sports, of course, sports has its own physics, and of course computer games also are based on physics principles. There is in fact a very nice textbook, I've forgotten actually, but it talks about using physics in programming physics games, computer games. These are examples actually. You at a school level, very small, even elementary school level, you can ask students to do very simple things. You ask them to observe phases of moon and draw them. You ask them to write the number of days with the number of phases. You can ask them to keep track of the timing of tides. Now you say, look, I'm in Delhi and we don't have any mechanism of observing tides, but newspapers at times, some newspapers do give the timing of the tides. Okay, and then if they write it and then they correlate with lunar phase, there would be somebody wants to say something. Okay, so they will be able to observe something, some similarity, some pattern, okay, some symmetries. Rainbow, I can't tell students that in the afternoon go and observe a rainbow. That won't be possible. So rainbow occurs only at certain times, or either in the morning hours or in the evening, early evening hours. So, and then the sequence of colors in primary and secondary rainbow. Now, these are very simple activity. Even small children can do. And they would enjoy it doing also. This is for physics. Actually, there are plenty of things you can do for chemistry and biology. The timing of sunrise, the day to day, starting with January 1st or whatever day school starts, you ask them. And you say, okay, with respect to north, just point your compass and find out at what angle sun was rising. Correlate with your latitude. See, it would be very okay. The timing of moonrise with respect to phase of the moon. These are very natural activities which doesn't require mathematics, serious physics. I mean, if they say activity based. Now, when you say that we have reduced the syllabus, just think about this. You can show a laser beam on a mirror and show how a ray is reflected. Then very simply you ask student to construct a ray diagram to show where will the image of point P be formed due to mirror. That would be a very good activity. It's not a very easy activity. And I'm telling you why, because I know that most of the teachers also don't find it very obvious to draw this kind of ray diagram. But it's a good activity to understand the formation of image. Yeah, here is the answer actually. So you take two rays and they are reflected, and then the observer finds it coming from P dash. So same thing you can extend for formation of multiple image due to combination of mirrors, reflection in curved surface, refraction at plane surface. Unfortunately in school, they teach that you have two inverted prisms. They would combine those colors and then you will see white light. But if you look at a parallel glass slab, you see actually they are supposed to split. They will never recombine. And then the question is that why don't I see colors when I see light coming through, white light passing through a glass? All right, interesting question. I'll not answer it. Okay, there was one question which people often ask. So we can ask students to construct this diagram. They say we talk about magnification in telescope, but we always show it by parallel rays. So we took the parallel rays, but inclined to the axis of the telescope. This is also a very interesting question. So if you see any automobile rear view mirror, it says the objects in the mirror are closer than they appear to be. Okay, so why is this written? What does this actually mean in terms of the kind of mirror, whether it is convex, concave, size of the image, where is it formed, etc., etc. Right, so that's a very interesting reflection. So if you ask students this question, they will have to really understand and analyze the whole process of image formation, correlate with what you have probably taught them about the way mirror image is formed in the mirror, and then the real situation where it is actually being used to see objects which are coming behind your vehicle. Then you can actually, the Huygens construction for reflection, refraction is actually there in the textbooks. I'm referring to NCERT textbook. But instead of actually doing it on the board, you can ask students to follow this ray tracing principle and understand reflection and refraction. This question we specifically created to introduce students to something which is happening in India at the forefront of research, which is giant meter wave radio telescope. So we took the data about the telescope, and then we said, okay, look, what would be the resolution you would achieve with this giant meter radio telescope? Why? What was the purpose of spending so much money to do this? All right. So this is it's not a difficult one, but it exposes them to something which is happening at the forefront, the purpose of doing it, what would we try to achieve it. Then students, of course, having gone through this, they may want to learn more about it and they may accumulate more information. So that is the joy you have communicated to them. This is, of course, a very simple one. In fact, one of the activity I proposed when they do gravity is called Bode's law. Okay, it's a sequence of numbers. Then you add 4 to each number, and then you divide by 10. Then you get these numbers. And if these numbers taken as astronomical unit are very close to the distance of planets from Sun. And then the interesting part is, in Bode's law, actually you take the t raised to 3 by 2, that will simply give you time period in years. If you take distance in astronomical unit, raised to 3 by 2 will give you time period in years. So actual distance, the one we get from Bode's law, and the observed time period, what we get from Bode's law, you can compare them. So it becomes a good exercise. No students will ever forget after doing this exercise what is Kepler's third law. You can ask them to plot graph. You see PV equal to constant. Most of the students don't know what it looks like. Then if you teach potential energy, gravitational potential, and the force, one goes as 1 over r, the other goes as 1 over r square. So they plot it, they would understand the difference between this. I mean, you can add e raised to x, e raised to minus x, all kind of graph. It's a good activity for them to be able to visualize. In textbook, we draw the graph, but we don't know why this graph. They just try to memorize as a pattern rather than knowing the meaning of that graph. In fact, a very interesting question in dimensional analysis, these dimensions which are never asked actually to students. But more interestingly, we created one of this where they have to match. But if you know the physics equations, Then this L by R and RC has dimensions of time. This LC is 1 upon root LC has the dimension of frequency. Epsilon 0 mu 0 is 1 upon speed of light square. So you can easily find out the dimension of these quantities without knowing even dimension of L and R. So, but of course, these are more for assessment. Now see here, somebody said that in school level we have really reduced the syllabus. No, Pani madam, I would be done in the time you have given to me. So,
No problem.
thank you for the patience. So this problem we created for school level students actually. We don't teach them maths, but we said that suppose if you have an arc carrying current, then the magnetic field strength will be proportional to the angle subtended. Then it would also be proportional to the current, and it would be inversely proportional to radius of the circle. All right. And then of course the direction you give by the right hand rule, etc., etc. We are communicating this information. Even if this is not in syllabus, I can still put this as a problem to students. Okay, because this is in a way a mathematical exercise, but by making them do this problem, I would have taught them a lot more about magnetic field. All right. So the magnitude of the magnetic field will be given by this. I'm sorry, there is a mistake. That by there should have been theta somewhere here. Okay, it says where theta is angle in degrees. It should be proportional to theta. So I should put theta somewhere. So I'm sorry for that typographic. But then this question is given to them. Then now you look, you have a bend and you have a current passing through. It gets divided into two circular arcs. So what would be contribution of this entire circular part to the magnetic field at the center? It's a very interesting exercise, I assure you, and you will be thrilled to know the answer if you carry it out. Now this is a question, when we say that we teach electricity, they don't know anything about household electricity. But just look at the simple question. Your coal costs ₹5 per kg, and it can produce 20 megajoules per kilogram in a power station. If the power station this 25 with 25% efficiency, what will be production of cost of 1 unit of electricity? Most of the students don't even know what 1 unit of electricity means. Okay. In Delhi, of course,
with the same problem, if we connect the nuclear energy production,
yes,
which
yes,
would be,
yes,
and
yes.
then compare with
Please.
this and hydrogen, then it gives a very comprehensive and very
Yes,
satisfying.
Excellent, excellent. I'm really happy that somebody has already put it in the right spirit. So we can communicate, teach them a lot of things without that being in the syllabus. And students will be excited to learn this. Now, when we talk about problems, does it have to be numerical? Then you see, this is of course 11, 12 standard. You look at these isotherms. Okay, these are isotherms of pure substance such as water. And then the question is, your liquid petroleum gas in a cylinder, cooking gas cylinder, also works on the same principle. Okay. So one has to explain what part of these isotherms would tell you, explain to you the working of that cylinder. There are more intricate questions you can ask, but it does not have to be mathematical. All right. So this is, you can call it as a question, you can call it as a problem, you can call it as an activity. It would lead them to interpret the graph, understand the graph, correlate with the actual device which are every day used at home. Of course, now we have pipe natural gas, but still, it is still, I mean, gas lighters. The smokers use those lighters. They also work on the same principle. So the explained working of LPG cylinder using isotherm shown, okay, etc., etc. There is another one, you have this phase diagram, T versus T diagram for water. You can try and ask students, how would a pressure cooker working can be explained using this? And what is the advantage of using pressure cooker? As I said, I'm not answering the question. That's not my purpose. I'm just exposing you. By the way, these questions, some of these questions We had put in an article in School Science, which is published by NCRT. I don't remember the article number and the issue. Okay, then similarly, you have a snowball which you form. So how would a snowball be formed? You have to explain it using these isotherms. So then you actually understand thermodynamics. Otherwise, it's an abstract. We teach them in classroom what is there in the textbook, and we draw this diagram and we say X, Y, Z, W, whatever. But they don't know what is the correlation in their life, where this physics actually works. All right. So thinking along these lines would actually, I think one of this problem is also there in exemplar problems for class 11. In fact, this problem I framed when I was just traveling by Air India flight some years back, when they used to show movies and they used to display temperatures outside, etc., while you are in the flight. So normally we have an isothermal model of temperature that you assume that temperature remains same and pressure varies exponentially with height. But what? So this is typically how a typical textbook would do. Even Halidares would show you how pressure is varying exponentially. But then what I did was I just recorded height versus temperature, just half an hour duration before it landed. So I'm assuming that in that half an hour journey of the flight, which would be around 200-300 kilometers, horizontally there is no change in temperature with height. I'm assuming. So that is my approximation. And then I have the temperature recorded versus height. All right. And with that, I'm trying to do the modeling of atmosphere. Now, this actually problem can be done by students at 12th standard level. This is no relevance to your CBSE exam, but it's a very interesting exercise, very insightful to understand. So the graph shows me temperature varying linearly with time, with height, right? And then, of course, with that, we go ahead and model not as an isothermal. We end up getting this expression for pressure. And this expression would actually, in the limit of gamma going to 1, would reduce to the exponential formula that we talked about earlier. But otherwise, this pressure goes as 1 minus Z upon 3.5 Z0 raised to 3.5, where Z0 is this RT0 by mu G. That's the scale height. I think this also was published in School Science. I don't know the issue. Now, this is a JE problem which I talked about. A very interesting problem. So you have a neutron which collides with a singly ionized helium atom and then gets scattered. And then what are the energies a neutron can have and what are the wavelengths which can get emitted? Very interesting problem. It does not involve any extraordinary physics. You need to know energy levels of singly ionized helium, which works just like hydrogen, except for factor of Z squared. You need to apply some scattering collision formula. And you have to understand that this scattering is not elastic. So when a neutron collides, it may end up exciting one of those higher energy levels based on conservation of energy and momentum. This was asked in JE 93. So this is a very, very interesting problem. As I said earlier, some problems will be very interesting. So you may create auxiliary problems to make them understand how to handle collisions, etc. You may give them auxiliary problems about the energy levels of singly ionized helium. Then you have to talk, what would you do with your equations if it is inelastic? In this case, it is inelastic, but we exactly know how much energy it can lose. It's not just inelastic for sake of saying inelastic. All right. So students have to be guided to understand inelastic process, atomic level, helium plus levels. Okay. So it would be an exercise in reviewing the Bohr model also. And then, of course, eventually, you know, what are the frequencies that can get emitted, what are the energies with which neutron can come out after the collision, etc. This is, of course, a computer-related exercise. We just take two waves, slightly different frequency. Okay, and Microsoft Excel is a very good thing to do. I think these articles are supposed to come in school science on use of computers in learning physics. I don't know the title. Use of spreadsheet in physics, something like that. So those two waves added, in Excel, you don't have to do extensive calculation. You can just drag the mouse and then plot the graph of the data generated, and it shows you the beats formation. The beauty of Excel is I just change one of the parameters and it will automatically change all the graphs which I have plotted. It will change all the data automatically. And students have Microsoft Excel free available on Android-based mobile. So you can make them do in class. Now I've taken two waves, one incident. See, the blue one is incident wave, the red one is reflected, and the green one is the combination of the two. And I've taken it 8 different times of the time cycle. All right. And now what I'm doing is all the green ones I'm plotting simultaneously. Although you will see graph with different colors, but they are basically the green color graphs, which are the combination of incident and reflected waves simultaneously. And see what it generates. It generates two loops. Okay, it is just the persistence of vision that makes us see a loop. Otherwise, these are the strings at different point of time. So that's a formation of stationary wave or a standing wave. So this is a very simple activity, but what we actually show to students as just the loops, but if they actually construct mathematically, doesn't take much time. I suppose 10 minutes they would be done if a teacher is well prepared to address this. Thank you very much. Now it is up to the organizer, Pragya Madam. If there is a time and people have questions, I will be glad to answer.
Thank you so much, Dr. Modi, for giving us this detailed scaffolding. Are there any questions from the participants? There is one question in the chat that is, I find difficulties in differentiating between application and analysis type problem. Can I have your account on it, sir? This question is from Mr. Rajkumar Parashar.
See, analysis means you are given some information, and out of which you filter out the needed information. I'm sorry, that's yes. Or you generate an analysis and synthesis. Get confused, but basically to turn out the information and generate by doing some calculation and so on. But application is the kind of graph I showed you, the pressure versus temperature, and you try to understand this process which are taking place in cylinder or in formation of snowballs or in pressure cooker. Okay, that's a direct application. This collision problem which I showed is an application when you are actually observing these processes in a nuclear reactor for people to understand and interpret. In fact, this is one of the way people trying to find the energy levels also. That is an application basically of the simple basic principles to understand the internal structures. Even in case of nuclear physics, this is how people trying to find energy levels of the nuclei. So that would be application of something which we know. The analysis is, of course, given information, you analyze and try to understand what is happening there. You calculate or you understand why it will move in this particular manner, why it will not move in this particular manner. That would.
Thank you, Professor Modi. I'm Rajkumar Parashari. I was the one who always remains confused with this type of issue. I mean, the problem is whether lies in analysis type category or the application type category. You see,
what difference does it make? As a physics teacher, what difference does it make? As I said,
it does make a lot of difference. Sir, it does make a lot of difference because we have been in NCERT and I've been teaching NCERT since last 30 years, more than 30 years. And you see, the CBSE question paper has its typology, isn't it? So we need to, as a teacher, I mean, every one of us should be able to differentiate between the application-based questions as well as the analysis-based questions. This is very important. And you see, I mean, when it comes, I have taken a few workshops on this as well. So see, I mean, when it comes like...
yes, sir, we've understood your question. Please allow Dr. Modi to answer.
Yes, it's important. Yes, I have a clear-cut answer.
See, my experience with one of the education board is that even plugin problems, they will call as synthesis phase or analysis phase or this phase or that phase. Okay, just by labeling, it doesn't make any difference. Okay, so as a teacher, if you are using this to understand, in chemistry, you synthesize. So you are given a couple of chemicals and you synthesize out of which a new chemical, a new information. And you analyze, you break it up and try to understand what are the different constituent part of the given chemical. That is analysis. So when you are given a problem and you want to find out certain information out of this problem, that would be analyzing the problem. But you want to specifically target to find one particular information, you have synthesized that information out of given one. All right. I know, unfortunately, these jargons become more important than the actual issues. So what I'm trying to say is that as a physics teacher, intuitively, most of us understand what we are doing. It is just that we are not fitting them into proper jargons. Okay, sometimes we do a lot of work, and to put it to people, we have to communicate, we have to put discover some words that this would properly explain. Otherwise, I don't know how to communicate what I have experienced or what I have understood. So I know the education board will tell you that, okay, these many questions on analysis, this many on application and so on. But let me tell you the secret. Whatever you say, like multiple intelligence, there won't be any problem where you can say that it is purely analysis or purely synthesis or purely application. Okay, it would touch upon all aspects. It would touch upon all aspects most of the time. Most of the time.
So Dr. Ahluwalia has a question for you.
Yes, sir. Please, I'm all ears for you.
Thank you very much, Professor Modi, for enlightening us. And I was really looking forward to your lecture. And I think it has really made me a bit wiser by listening to you. Am I audible, sir?
Yeah, you are audible.
Okay. I have a few things, if you can enlighten us on that also in mind. And that is that even Feynman, when he was talking about problem solving, he raised a very pertinent question there also. And that was that our problem is that the number of students whom we want to teach, that is also very, very large. Though one-to-one is the best way to do such a thing. And today when we have the technology and the way you have reached out to us, I am in Shimla, somebody is in Pondicherry, somebody is in Shillong. I think this has made us make use of these technologies in a very, very imaginative way. We as IAPT, what can we do to make use of technology to push these kinds of ideas further to the unreached? I'm particularly underlining this word, so that they also become, alive to such things. And the majority of, students who come in basic sciences, they come not through IIT entrance examinations or NEET examinations, but they come through as leftovers from those things. And I think they must be taken care of, because majority who are coming in that kind of a stream are not, say, because they didn't get marks and that's why they should be underrated. They are as good as those students, provided they are given this kind of a exposure which you were mentioning. So I would like to request you, please tell us how we can really move forward. And as the person who has been given responsibility to take care of IAPT, what kind of programs we should initiate to really take care of these, particularly the idea of flipping the classroom itself, where such things can be done and students can be made to, read something the way they read their textbook, or see something the way they read their textbook. Thank you.
Yes, sir. I'm glad you have been really paying attention to everything I said. For example, I'll tell you, in Mumbai University, first year BSc, our classroom is of 120 students. But when they come for practicals, they come in group of 20. And in a year, they have to do some 20 experiments. And normally we have plenty of time for those 20 experiments to be completed. So I actually made a suggestion that since there in the laboratory, the ratio of teacher to student is 1:20, we should actually conduct some tutorial sessions. But my suggestion was shot down saying that where there are practicals, there is no scope for tutorials as per UGC guideline. I have never bothered to find out whether that was true or false because I have no interest in confronting anybody. But I thought my suggestion was very practical and we could achieve a lot of things with this possibility. At Mumbai IIPT, every year, as a part of our summer program, we conduct a short problem solving workshop, which is, I cannot classify that as a problem based learning workshop, but we do try to expose students to some interesting problems from different area of physics within the limitations we have. This, of course, is not a possibility with the online mode. In online mode, of course, as I am part of those initiatives, NCERT is going to put a lot of things online available to students in terms of demonstrations, in terms of some augmented reality, and so on. So it should reach people even in the remote area. But this experience which happens between a teacher and student, it has to happen between teacher and student. And now their online, I don't know, would be effective. At least as I perceive at present, I am not able to see it becoming effective. I have tried in my own way wherever possible, but that one-to-one interaction, that physical presence, where you can say the aura of a teacher touches aura of students, that has to take place somehow. Now that in an online mode doesn't happen. As IIPT, of course, as we do a summer program in one sub RC, can be initiated in others as per their requirement and as per their local needs. So such things can be taken up. And since IIPT encompasses a big pool of physics teachers who are also part of the university system, it should not be difficult, because whatever decision takes place in a university system are with the consent of the practicing teachers themselves. So if they are part of IIPT and they can be, if they are convinced that these things should come into mainframe education, I mean, particularly when I say that, when I suggested that in labs we have 1:20 ratio, and therefore we should have a one session to be converted into tutorials, that would go a long way for students. It was a very practical suggestion. So I think a lot of things can be implemented, but it requires willingness to do that.
Sir, there is one proposal which
No,
government
wait.
Yeah.
Let Professor Ahluwalia finish.
Okay, sir. Please go ahead.
Sir, may I continue?
Yes, sir.
Yeah. Okay. What I want to tell you is that there are few other things also which are in my mind, which I would like to share with this audience which is sitting here. Is it possible that we create a problem sheet, like a tutorial sheet, say every month, and float it at different levels, say at class 11 level, class 12 level, plus one BSc part 1 level, BSc part 2 level, BSc part 3 level, and engage various teachers to take care of that problem and do it in their environment, right? So this is the idea which if you feel can be initiated, and we have a website on which it can be put. So I would like to really have your comments on this also.
Yes. We can initiate a process in that direction. I mean, how How exactly detailed can be worked out, that I can't answer at this point. But I think if members of IIPT are willing to take that up, it's a good thing which you have suggested. I'm all for it.
Ma'am, may I
So-
ask a question?
Thank you very much.
No, let Rosa Ahluwalia say that he's done this.
I think Professor Ahluwalia has said what he wanted to probably. He's
Okay, no
switched
problem.
off his
No
video.
problem. Yeah. So
Yeah.
then,
So we have another 5 minutes in which we have to conclude. So some Aradhana ma'am, you wanted to ask something.
Yes, ma'am. Thank you. Thank you, sir, for this session. First, sir, my question to you is that I've just started my career as a PGT physics person. And when I want to visualize the different concepts of class 11th and 12th physics, I feel that the technology is going to give me the direction, the various technologies. I want you to give me some directions so that I can visualize those concepts in a better way, and please broaden my spectrum of understanding for visualizing things to my students.
okay.
The law.
I'll tell you. When I started teaching, I started my I took up the teaching job immediately after I finished my MSc, as a equivalent of PGT only. We call it +2 teacher here in Mumbai. And I used to do extensive preparation, solve problems from Halliday, Resnick, etc. Because something which I was lacking, which I was not exposed to as a student. But I thought I have to do this so that I become better teacher and I can make my students better students. My father one day just looked at it and he said that, why are you working so much? You already have passed your master's degree with first class. You know everything. Why you need to prepare so much? Then I said, look, I have to learn so many things before I go and face my students, because the system has actually said that, okay, look, you are masters in your subject, but I think I have a lot to learn. So that was at back of my mind, and I made sure that I keep learning at every stage of my life, and that's what eventually evolved into what you saw today. So I think for a beginner, this is an idea. You try to read, you try to solve some of these interesting problems yourself. And it doesn't matter, my experience with +2 teacher at many places, I'm sorry, no offense to anybody, is that most teachers are more interested in ready-made solutions than try struggle themselves. So I think more you struggle, more your faculty of visualization, analysis, everything opens up. So it's a very important thing. Everybody has to struggle. When people do physical exercise, they struggle, their muscles develop. So more you struggle with your mind when you try to solve problem, more your faculty to analyze physics problems will develop. That's my answer.
Thank
So,
you, sir.
So
Actually-
may I
Actually,
add
one
something to
small
this?
question, Pragya
Just a
ma'am.
minute. Just a
Yeah.
minute, please, sir. Just
Madam-
1 second.
Madam,
So may I add something to what Aradhana ma'am asked you?
yes,
Yeah,
please.
please.
Yeah, so actually, I just wanted to add that on Veshika platform, there are a lot of programs which are going on for teachers, and you could join them. In fact, one of the programs is Physics Pe Charcha, which happens with Professor H.C. Verma every month, where we are showing very short 1-minute videos where some life event is shown, like maybe just a balloon which is stuck to the wall, or maybe specs in which you see two images of a tube light, and then you analyze and then apply a theory and answer the MCQ questions. So first the teachers themselves have to appear for this model NAST test, and then they are eligible for participating in this charcha. And teachers who are new in this profession get a very good exposure of how application and analysis both can be done, as Rajkumar ji was asking. So that is one thing I wanted to tell you.
Yeah.
Can I speak, Pragya ma'am?
Yes, sir.
Actually, I would like to draw your attention because we have got circular from the government that we have to initiate innovation and entrepreneurship skill nurturing the schools. So framing the school innovation committees. And I would request that Anvesika should come forward and we can use the expertise of Anvesika to encourage teacher as well as students in the area of innovation. So can we design some set of tools or instrument in which one can be used to perform or demonstrate more than 3 activities, and then we can provide it as a hands-on to the teacher and student, and with the instruction and opportunity that they can use it to design as whatever they can, and then when they come to design 1 or 2 or 3 type of things, perhaps we will be able to give little challenge and will give opportunity to innovate. So it will be a kind of simulation. So what we can do at the platform of innovation and entrepreneurship, and how Anvesika can help teachers and students and schools to sync with the new policy which is coming to nurture innovation and entrepreneurship skill from the beginning, that is from the primary.
So, Dr. Modi, I think, may I take this question with your permission?
Yeah, please.
So, Prithvi sir, even before the government came out with this policy, we were doing that. And I think professors and school teachers involved in IAPT have been doing it for years.
That is why I raise it, because now we need your help.
They've been doing it for years, even before I came into education. I think IAPT Professor Khandelwal instituted IAPT with that outlook only. Professor Saraf, Professor Pradhan, there's so many innumerable teachers who have been doing this. And if you join the IAPT group, there are a number of teachers there, Professor Nand Krishnan, and so many people who have been doing these demonstrations, innovative ideas they have been bringing forward. And as far as Anveshika is concerned, we have lot of innovative demonstrations which we are doing with teachers and students as well. There are experimental challenges. You will be glad to know that for last 2 years, when the schools were closed, under National Anveshika Experimental Skill Test, we have given 4 experiments each year to about 1,600 to 2,000 students to perform completely using things available at home, but they are full-fledged experiments, physics experiments, which have been performed right from children of class 9 to MSc level. And there the children have just been given a problem, and then they've just been told that you could probably use these equipment. They gathered those equipment, and each person had a different object as an equipment, because whatever was available at home, for example, पूड़ी तलने का झरिया जो होता है, उसको लेकर हम oscillations, उसका moment of inertia, time period of oscillation, all these things have been found out. And so, but the thing was that children were not bound by the apparatus in the lab. They designed themselves the experimental setup to solve a particular problem. And out of that, they did data collection, they plotted data, they made inferences out of that. They tried mathematical modeling as well over there. So this was done without the binding of the school lab. And each child came up and gave us such encouraging feedback that they felt liberated and exhilarated, because the whole family, the teachers themselves got into it. Since the solutions are not there on the net, there was no set procedure. So together it became a celebration of experimentation. So anybody who is willing, we are not really interested in giving kits. We are really interested in people coming together and designing solutions for a problem using whatever material is at their disposal. Because whenever we have given kits, we have found that people have kept them in the cupboards and have not used them. Nor we believe in putting information in form of videos. Otherwise, the teachers go and show those videos in the classroom rather than making people participate and get the excitement. The excitement is out of participation only. So I suggest that we invite you to come to our platform and contribute your ideas and make it richer. Thank you.
Thank you, ma'am. Thank you. I wanted just to discuss because this is something which is coming. So your
So
expertise can be
the whole
used for-
IAPT is already on the job, I think.
Thank
Yes, sir. Thank you.
Thank you, sir. Thank you.
So are there any more questions? We just have only 4 minutes because I have another meeting to start. So please.
Madam, two hands are raised. Aluwalia sir and Surujji Agarwal.
Yes, sir. Professor Aluwalia, you want to ask something?
Just one, ma'am, and that is, in fact, that there are, many things which are there in the environment. When I say this, means there are lots of things which have been made around by people, well-meaning people. For example, Vikram Sarabhai Science Center people have designed many experiments which can be used. They have maybe Madam Pragya will not agree with that, very good kits, but they can be given to, schools as innovative labs. For example, they have also designed a tinkering kit in the same spirit as we are talking of tinkering labs itself. I think it is worth going through those also, because IAPT's duty is also there to curate good things for the members who are part of our community. Sometimes, people may not find the kinds of things which they are looking forward to, because nobody has really validated those, whether they are good for us or not. Maybe one can initiate that kind of a validation process also at the level of IAPT, so that when people say go and look at those things, they may find or feel inspired that, oh yeah, they can also construct these things in their own labs also. And doing it before their students, it will be a wonderful exercise. Not just giving kit to the student, but doing that kit in front of the students itself.
Yeah,
And then,
that actually motivate, that inspire, and this all will fulfill to some extent, because even we could have 2 or 5 students in a mass crowd, that will be even enough. Because now we are finding that the children are not so much excited and interested when they are just being bombarded with instruction. They
so
need
this was
something.
my point, ma'am. I think with that, I would once again thank Professor Modi for giving us a kind of a wonderful lecture. And I think this should inspire many people in this audience, as well as when it will go on the cloud, it will inspire many more. Thank you very much.
So last question by Suruchi ma'am, who has raised her hand.
Thank you so much, ma'am. First of all, I would like to thank you, Modi sir, for such an enriching session. And Pragya ma'am, you also for always conducting and organizing so enriching and enhancing sessions for us. Can I have one more request from you, ma'am, Pragya ma'am?
Yes.
One more session can we can request Modi sir to have with us, wherein he can actually give just which examples are already shared today. But as he designs so realistic questions always, or which are really connected with our day-to-day life, so a core session purely on his questions, what he designs. Can we have such session from Modi sir?
बिल्कुल, आपने actually मेरे मुंह की बात छीन ली. That is what I was just going to request, that Dr. Modi, you've given us a scaffolding. Now for each step, could we have more decoding? Because I think, as you, in one of the slide, you said that it is, while solving the problem, is not just putting the number, it is the cognitive process that is going on in solving the problem. We should have a look at that. but I'm sure many of us don't understand those things in great detail. So if it could be exemplified in greater detail, I think that will help the newcomers as well as even experienced teachers to have a new look at our own cognitive process that we go through when we do these things in the classroom. So if you could agree to that, we'll be very grateful.
I haven't
Yes, yes,
tried
sir.
that ever,
Actually,
but we can try. I don't know how effective that would be online, but we can try.
Yes, sir. Thank you so much, sir. And I'm really extremely grateful to you for finding time today. And thank you, Professor Ahluwalia, for such good suggestions. And I stand corrected. Yes, the kits which are made with so much of thought, yes, we should be pointing out attention towards them. And I hope that they will be used. That is all my humble submission is, that they just should not remain locked. And as you said, teachers should find time to demonstrate and involve students in working with those kids. So thank you so much. And we look forward to more such sessions with all of you who are present here today in this session. And now I have to close this session absolutely because we have to start another session. Thank you so much. Thank you all.
Thank you, madam.
Thank you. Thank you, sir.